Q2. Q1 is the bottom one. Figure out all right.
Good afternoon. I'm Don Savage, Public Affairs Officer for the Office of Space Science. And welcome today to the Goddard Space Flight Center and the latest of our Comet update briefings here at Goddard. Today we have a major announcement to make, major discovery by the Hubble. And our top news this morning, we will also have Dr. Rene Pronget, who will tell us about how cometary debris is making the Jovian aurora light up. And Dr. Lucy McFadden will give us a worldwide wrap-up, and Dave Levy will be here for discussions on the observing. I'd like to go ahead and introduce our panel right now. To my left, Dr. Roger Yell with the University of Arizona. He's a scientist from the University of Arizona and a member of the Hubble Space Telescope spectroscopy team. To his left, Dr. Rene Pronget from the Institut Astrophysique Spatiale in Orsay, France. She's a scientist from the French Institute at Orsay and a member of the HST Upper Atmosphere Imaging Team. In the center, to her left, Dr. Steve Marin, our moderator for today. He's a senior staff scientist at the Goddard Space Flight Center. To his left, Dr. Lucy McFadden, University of Maryland and University of California, a visiting professor at the University of Maryland and coordinator of the worldwide Comet Observing Campaign. And to her left, David Levy, co-discoverer of the Comet and longtime Comet observer. Welcome, panelists. I'd like to turn it over to you, Steve.
Thank you, Don. Good morning, ladies and gentlemen. For those of you who had the advanced schedule, I'm not Eugene Shoemaker, and I won't have any explosive results for you. It is a pleasure to be here again. I've lost count of all these fragments, but fragment P2 should have struck within the past hour. And as I think you all know, many of you led with it yesterday or this morning, the first of the three other big fragments, the Q, R, and S, that will be hitting Jupiter at intervals of approximately equal to its 10-hour rotation period, so they'll hit at nearly the same spot at 10-hour intervals. That will start at about 3:32 Eastern Daylight this afternoon. We'll hear a little bit more about that later. Now for this, what I personally as an astronomer think is a very exciting scientific result to emerge from Shoemaker-Levy. There's more to it than just a big show. We're fortunate to have Roger Yell at the University of Arizona tell us about this Hubble spectroscopy result.
Well, good morning. And as you all know, there's two sorts of information that the Hubble Space Telescope's been gathering. What you've seen mostly is images where you see the entire planet and the impact site at a very specific color, a specific wavelength. But also with the spectrographs, we look at one spot on the planet, but look at all the colors, all the wavelengths simultaneously, and that's what we call spectroscopy. So I'm going to report on some spectroscopy results. You can see on the monitor, I believe, an image of the G impact site, and it's the spectroscopy from the G impact site. We knew that was going to be a big one, so we pointed the spectrograph there several hours after the impact. And in the next, could we have the next graphic, please? The arrow is pointing to the location of where our spectra were obtained.
Spectrograph was the faint object spectrograph.
Faint object spectrograph. That's right. I don't know how to get that on the screen.
Next graphic, please. They'll have it up in a moment.
Okay, and what we're going to see in this graphic is the distribution of brightness from this spot as a function of wavelength or color. Now, different molecules. Okay, there it is, and I'm going to be talking about.
That's ultraviolet light.
This is ultraviolet light. The wavelength is probably hard to read off that scale, off the image there, but it goes from about 150 nanometers to 3,000 nanometers. So this is light that doesn't get transmitted through the Earth's atmosphere. You need to be above the Earth's atmosphere to observe it, and that's why we use the Hubble faint object spectrograph to make these measurements. So what we see there is the ratio of the light from Jupiter after the impact to the light from Jupiter before the impact. And you can see that the ratio is not 1, which tells us right away that something's changed. It's less than 1.
If it were 1, it would be a straight line, right?
If it were 1, it would be a straight line across the top of that image. It somewhere varies from about 0.2 to, I guess, 0.7. So what that tells us is that these spots are darker in the UV after the impact than they were before, and we knew that already from the images. It's no surprise. But if you look very carefully at distribution with light with wavelength, you can look for molecules. Molecules will absorb at specific wavelengths, specific colors that are their own signature. So one molecule will absorb at one wavelength, another molecule will absorb at another wavelength, and by analyzing this, you can identify some molecules. Yesterday, Keith Knoll told you about ammonia, which happens to absorb light right around 2,000 angstroms, which is the minimum in that spectrum there. And there's ripples there. If you look carefully, you can see ripples in the spectrum, which are characteristic of ammonia. What he didn't show you yesterday were the larger ripples to the right at about 270 nanometers. They're about, well, I think they're fairly obvious there. It looks sort of like fish bones or something. And that was very exciting when we saw that yesterday, but we had no idea what it was. And so we spent the last 48 hours or so trying to figure out what this molecule was. And it was something of a mystery. There are a few clues that you can that we went by in the spectrum. First of all, it's a very regular spacing of ripples in that, and that tells you that it's a simple molecule. Secondly, the ripples are close together, and that tells you that it's a heavy molecule. So armed with that, that eliminates some number of molecules in the universe. But I should have said, first of all, that we had expectations about what we were going to see. We knew what molecules to look for and where to look for them, and we didn't see those. We saw ammonia, which was expected, but this is something that was totally unexpected, so we didn't recognize it right away. We had to go off and search spectra of all the molecules that we could think of to find out what this was, and none of the simple ones matched up. So we got more and more perplexed and kept looking. But as I said, we had these clues. It's heavy and it's simple. And finally, about 3 o'clock in the morning, we started zeroing in on sulfur. And in fact, those features are a very good match to the spectrum of sulfur, sulfur gas, S2, the S2 molecule.
Sometimes called the dimer, the two similar molecules, two similar atoms in the same molecule.
No, it's not.
Can't get them all.
It's a diatomic molecule. It's anyway. So that's a definite detection of S2 molecule in the atmosphere of Jupiter. Now, also there's some more structure around. In addition to ammonia at the shorter wavelengths where that big minimum is, and by looking carefully at that, we think that there's probably some hydrogen sulfide, H2S, in the spectrum at that location. That's not as clear-cut as the S2, but nevertheless, it may be there. The spectrum is consistent with the presence of hydrogen sulfide. It might be possible to explain it with something else also, and we're not sure of that yet, but it seems to be consistent with hydrogen sulfide.
Okay, thank you, Roger. S2 was found in Comet IRAS-Araki-Alcock, I believe.
Yes, that's true. It's been seen in one comet before. Sulfur is seen in most comets, I believe, although not in the S2 molecule. And we're going to have to do some work to try to determine whether this sulfur, there's of course sulfur also in the atmosphere of Jupiter, and it's not obvious just from this result at this point whether the sulfur is from the comet or from the atmosphere.
Okay, and of course, as everyone knows, Hubble doesn't just take spectra, it also takes images. And one of the areas of the study of the comet that I think we have not heard about in these briefings thus far, because we haven't had a lot of news in that area, has to do with the effects involving the magnetic field of Jupiter and the interaction with the comet. And Dr. René Pranger from the Institut d'Astrophysique Spatiale in Orsay, who can pronounce all those words much better than I, is involved in the Hubble imaging team working on these problems. And tell us what you've been learning.
Okay. It's right that one of our major interests in the observation, on top of studying the upper atmosphere of Jupiter, was to understand the physics at work in the magnetosphere. And since the magnetosphere is not a trivial object, I will just briefly put it into context before I discuss the observations. Jupiter, like the Earth, is a very strong magnet, and the magnetic field lines delineate, carve a cavity in the solar wind, where a lot of plasma, which plasma in our JACON is a tenuous ionized gas of electrons and ions are confined. This cavity is very extended. It's millions of kilometers in diameter. It's 5 times the sun. And the tails extends still farther. At times it goes up or down, as you like, to Saturn, which is 5 astronomical units. So the magnetosphere of any magnetous planet is a huge natural laboratory for plasma physics, and that's why we are interested in that. Unlike the atmosphere that you have seen a lot in the last few days, the magnetosphere of Jupiter is not visible, practically invisible at all wavelengths, except in the decimetric radio wavelength, which has been used to discover the magnetic field of Jupiter. So we can only study the magnetosphere by deep space mission in situ measurements or by monitoring remotely the auroral emissions. And that's why we are interested in that. The aurorae, that again are like the aurorae on Earth, which are also become polar lights, they are at the end of the chain of processes in the magnetosphere. It's at the place where energetic charged particles, so electrons and ions, finally fall, and we say precipitate on the top of the upper atmosphere. And the energy of the collision of these particles on the constituent species of the atmosphere makes the atmosphere shine, either in the UV or in the infrared, not in the visible spectrum. And you can see on this picture, which is on top, which is an image of the WIFPIC-2 camera, about around below 2000 angstrom in the far ultraviolet. So it's not visible just by naked eyes. On both sides, on the polar region, north and south, you can see these lights, kinds of ovals with spots, which are the footprint of magnetic field lines which go far away in the magnetosphere of Jupiter, and where the particles which are along these magnetic field lines, they fall down and they impact the atmosphere, they make it shine. For us, it's a signature of what happens in the magnetosphere. We have been using 2 cameras. We have been using the WIFPIC-2, which is the American camera. We have been also using the faint object camera, which is the European camera on board HST. This is an image which has been taken on July 13, before the impact, 2 days before the first impact. And already 1 week after the first dust, sufficient dust was inside the magnetosphere that we could expect some effect from the dust with the plasma in the magnetosphere. There had been a lot of prediction of what could happen in the magnetosphere. Some effects could come from the dust in the leading edge. Some could come from the comet of the comet itself, interfering with the plasma in the magnetosphere. And we could expect to see some effect even before, like precursors of the impact. In this image, you can see also the North Pole, the South Pole. We cannot see the whole.
Can we have that graphic back, please?
So we cannot have the whole planet because the field of view of the faint object camera is much smaller than the field of view of the WIFPIC-2. But the interest of the faint object camera is that you have a very, very good spatial resolution. You can get very faint details, so they are very complementary. And on this graphic, you can see what we are somewhat frustrated because we didn't see anything spectacular before the impact. We already had images of the aurora. They looked like that, except that the North Aurora consistently looked somewhat fainter, maybe at times much fainter than usual. And it looked fainter than the South Aurora, which is this nice necklace on the lower panel. We got the same kind of result with IUV. We have been monitoring the aurora with IUV for several weeks already, and we found that the North Aurora was weaker. We cannot tell why. We cannot understand that. We expected, if any fainting, we expected it in the south, because the dust could be inhibiting the processes would give rise to the aurora. We get it faint in the north. Maybe it's just coincidence, but we have to.
But maybe it's brighter. Couldn't it be brighter in the south and it's being enhanced by the dust from the comet fragments?
Oh, it's clearly fainter in the north. We had a lot of trouble getting the north.
Okay.
Normally, you can see an oval, which is around, you have a spot in the middle. This is very, very obvious in all the data.
And you find this both with the Hubble telescope and with the International Ultraviolet Explorer.
Right, with both. So we can tell for sure it's an effect of the comet, but it may be an effect, a general global effect of the dust in the magnetosphere. Then we got this nice image on July, 2 days ago, was it July 18,
Yes.
with a WIFPIC 2 that I hope we'll get here on the screen.
Next graphic, please.
And you can compare this image to the one we got before. You can see the aurora on top, the north. It's still fainter. You can see the left edge. You can see the aurora on the south. And below the north auroral value, you have two bright spots, which are very low. For us, it's very low latitude. It's totally unusual. It was not unexpected. I can tell there had been predictions that maybe the comet plasma could be ionized. This could drive a current, and it could enhance create new.
Okay, so the two bright spots you're talking about are the upper left and
the upper left, on just at the footprints of these new magnetic field lines which have been drawn now. Oh. And this is quite new. We never saw that. We never saw any aura below what is the one you have seen on the previous two graphics.
So that's, to make sure I understand what you're proposing, you think that material from the south pole where the fragments are impacting might be drawn through the magnetic field lines up to the north pole?
Right, that's what I'm thinking.
Wow.
There have been, well, if you look back to the prediction that has been made, it's clear that we expected some effect of the ionized plasma in the material in the comet to interact with the plasma in the magnetosphere. But we didn't know what we should do. And in any case, we expected to get something in the south, not in the north. And we worked out a lot to get the possibility to have closed field lines, because the magnetosphere, at times, the field lines, they're open to the solar wind. So in that case, something which happened in the south do not have any counterpart in the other hemisphere. So we worked the geometry so that we can get a closed field line with a footprint in the north, visible also from Earth.
So the north and south are connected by the magnetic field.
In that case, they're connected. They're connected, and on top of that, the footprint of the north is in front of, because the field line is distorted in the meridional plane. So you can see the footprint in the south, it's just right at the limb, but you can see it's already 30 or 40 degrees on the limb
If you think
from the limb on the north.
If you imagine it's kind of a bar magnet inside Jupiter that is responsible for magnetic field, in that model, then the bar is off-center and tilted.
Off-center, tilted, and
that's why it can be in
bent
back. These lines can be in back on the south and in front on the north.
So we are lucky. Well, not only lucky, we worked it out. And we get this bright spot in the north, but we have nothing and we didn't get anything, except maybe you can see something very, very faint and diffuse at the footprint of the in the south of the larger field line. We cannot tell. Well, that's probably not precipitation of particles. We do not know what it is. It may be related. But this on the north pole, it's necessarily energetic particles. So something happened. Some material from the comet itself was liberated in the south pole, accelerated by some way along these magnetic field lines, and fell into the northern hemisphere, like an iron gun, in fact.
Now, Renee, would these be visible in visible light where our eyes are sensitive?
It's far ultraviolet. The auroral emission, I mean, the emission collisionally excited in the atmosphere of Jupiter, they cannot be seen in the visible, only in the ultraviolet from it depends on the composition of the atmosphere. On Earth, it's visible. On Jupiter, it's mainly from hydrogen or for hydrocarbons. And it's either ultraviolet or infrared. Unfortunately, you can see them in the visible. So that's a major, I think it's a major discovery. We have to understand what happens. We have two options so far. Maybe there are other options open, but we thought of two. Either the material was liberated after impact, and we got it along the field lines, and we see it in the north, and that's why we do not see anything in the south. Or another possibility, which was predicted, in fact, and I think I should send an email to Dr. Wing-Ip. We have published a paper very short ago, telling that within one Jovian radius, we have the conditions so that the coma entering before impact could create a current along the field lines, which would give the condition for such an effect to appear.
So you have to do more than just throw stuff up from the impact. You have to have an electrical or magnetic process that accelerates these electrified particles and drives them up the magnetic field
You have,
line.
you have to get like an electric circuit, and then you have to have like kilovolts of potential drops to accelerate the particle to high
thousands
energy.
of volts.
Thousands of volts to accelerate the particles. So it's not an easy process, and we have to work on that. And it's a lot of modeling probably, and we learn a lot about the plasma physics in general and Jupiter in particular.
Great. Thank you, Dr. Prange. I think these are two really fascinating findings from the Hubble telescope. And we had an assist from the IUE. I'm sure we'll be hearing more about IUE as the week goes on. Now I have to tear myself away from this orbiting observatory. There are, we used to say there were hundreds of telescopes looking at Jupiter this week. Now, from the reports coming in that amateur astronomers and the public are streaming into observatories, science museums. I think Lucy McFadden told me this morning hundreds of people are coming to the University of Maryland Observatory over here near Adelphi. There probably are thousands of telescopes looking. They won't all see aurora. You have to look in ultraviolet light. But what are the telescopes on the ground finding, Lucy McFadden?
Well, actually, Steve, with that introduction, I think I'm going to let David Levy talk about the hundreds of telescopes that are being pointed toward Jupiter, and let him talk about what the amateurs are seeing and the role they can play in the science, and then I'll come back and
we'll go to
fill in
David.
on ground-based.
Okay, this is almost a contest as to which is the best surprise, which is the biggest surprise of this whole magnificent week. And I can't say that the fact that these dark spots are visible for virtually everybody to see is the biggest surprise, but it sure is one of the biggest. Nobody expected this. We have some very large spots on Jupiter. They seem to be the brightest ones at the latest that I heard still is the one from the impacted fragment G. And it seems to me that no matter what part of the world you're on and no matter what area you're watching, by now there are enough of these spots that no matter where you are, when Jupiter is in the sky after dark, you will probably be seeing some spots.
You didn't mean brightest, most prominent. It's actually dark for...
I meant darkest,
Okay.
yes. When I say brightest, I mean darkest. Thank you, Steve.
It's his comet, he can put it anywhere.
No, the one report that I got from a professional astronomer who actually began as an amateur and still has his original telescope is from Clark Chapman of the Planetary Science Institute. He said that the spot from fragment G in his years of observing Jupiter is the most obvious feature ever to appear on this planet. And he has challenged over the internet anyone to argue that, and so far nobody has.
He sent me to the telescope last night, and it was pretty spectacular. So
Yeah,
I looked directly through the eyepiece, and there it was. So
Yes.
I encourage everybody, including all the crew and everyone doing the support work for all this event.
Now, Lucy, I
That's what
forgot to say that we have, and you're going to tell us about this, we have more than just telescopes on the ground and telescopes in space. We have something kind of part way up, isn't that right?
Yeah,
Yeah,
but let's
yeah.
let David finish with his points.
Yeah, I think it's hard to tell at the moment just why these spots are so prominent. One of the theories to explain them has to do with these are comet dust or a form of soot that is from the comet. There are other theories, but this is one of them. It's very important to emphasize that if you are an amateur astronomer, if you have any experience at all looking at Jupiter, any experience, these spots should be extremely easy for you to see. If, however, you have never looked at Jupiter before, my recommendation is that you go to one of the many star parties that are being organized by planetariums and amateur astronomy clubs all over the world right now, and get someone to point the spots out to you. They're very easy to see, but if you've never looked at Jupiter before, it helps if you get someone to point them out. This is an extraordinary thing. These spots are major effects from the collision. They're visible to anybody. The philosophical question is that if the comet had never been found, right now people would be seeing one spot after another appearing on Jupiter.
They'd be wiping off their lenses.
What would you say? What's going on?
That's right. They'd wonder what's going on. Probably the visual observers would have been spotting them first. If there had just been one spot, if the G impact site had been the only one, someone might have said maybe there was an impact. But these spots are now forming all over that area of Jupiter. And they would say maybe it was an impact, and they'd say, no, how could you possibly get so many impacts in the course of a week? And nobody would have
I guess
this
it's
out.
entirely possible that a comet we hadn't discovered yet could hit Jupiter and make a spot that large.
Yes,
Particularly if it,
yes.
I think we're lucky that these guys were watching and found it. So.
So this is the time to get out, and if there's ever been a time to get out with a small telescope and look at Jupiter, ever since Galileo first observed Jupiter through a telescope in 1610, this is the time to do it. This is just a marvelous time to be looking at Jupiter.
thank you,
Well,
David.
can I just mention that there are interesting, you probably talked about this earlier in the week, but there's interesting strings of craters on some of the satellites of Jupiter, which have been theorized to be due to a similar process, the breakup of a comet falling upon one of the satellites.
Yes.
And it may have occurred to someone that was similar to...
So that the multiply split comet may not be such a rare
That's right, yeah.
phenomenon.
It might have occurred, and that's a good point.
That could have happened any time in the past 4.5 billion years.
That's
But
true.
there is even one of these crater chains on the moon. On top of the crater Davy, there's a series of these craters.
And that's getting pretty close.
Yeah, but these did not hit Jupiter all at those crater chains hit Callisto or the moon all at once, all within a few seconds of each other. These are things hitting over the period of a week, and to make that intuitive leap to get the only way this could have happened is that a comet passed near Jupiter earlier, at some earlier time, broke apart, completed another orbit, and then hit. And if someone had come up with a theory like that, he or she would have been laughed off the stage.
It would be a
It's a rare
string of
event.
implausible events.
Yes.
All of which, however, we're seeing occur now.
Yes, that's so what
Okay.
the amazing
I think we
thing
need to
about
get
this.
on to
Yeah.
Lucy's report, leave room for questions while we have the satellite.
Okay. We have some more images from ground-based observatories around the world. The first one coming up is from Lick Observatory from the 120-inch telescope there. It is an image taken with speckle imaging, which is a process that astronomers and members of the Department of Defense have both been developing over the years. And with speckle imaging, they have they use computer. They use complex computer algorithms to clean up the noise and improve the spatial resolution of the image. And as you can see from looking at this, the parallel cloud structure is quite prominent, and it's
Very well defined.
higher, yes, better defined than in most of the ground-based images. Not quite as clear as the Hubble, so it's not as good as getting above the Earth's
That's
atmosphere.
the adaptive optics project led by Dr. Claire Max in Lawrence Livermore National Laboratory.
Good, thank you, Steve. Then next we have some more observations from the Keck Observatory, where NASA and the NSF have contributed to building the instruments from which we're taking these measurements, and we have a mosaic. Now these are 7 images. Ignore the time difference. Each image is a different wavelength, and in the upper left corner we start at a wavelength of 1.2 microns, and we go across the dark one, the third one on the right, is at 2.3 microns, and we continue to go to longer wavelengths, and the final one on the bottom, where Jupiter is the darkest, is at 4.2 microns, I believe. Now, the importance of this, all the features appear as bright spots, so they're still radiating thermal heat. They're just radiating the heat from the impact sites. The advantage of using different wavelengths is as the wavelengths get longer, the wavelengths penetrate deeper into the atmosphere. So this is like a stratogram. We're looking at the layers through Jupiter's atmosphere.
So I guess besides the fireball that came up that Gene Shoemaker's been talking about from the simulations, you still have some hot material down under that's glowing
yeah.
after days and after the event.
Right. And this is important once we can interpret these and correlate the information from the different wavelengths. We hope to be able to determine how deep the projectile went into the atmosphere. I don't have any numbers, and we haven't really understood that yet, so I can only present it in a generic case. We have a report from the Kuiper Airborne Observatory, which is it's a C-141 cargo aircraft. It's a really spectacular aircraft. It's been compartmentalized. They blocked off one part of it where they placed the telescope. There's a 36-inch telescope in this compartment, which is pressurized, and they cut a hole in the side of the cargo plane. And they point the telescope out the hole in the plane. Now, this plane flies at 41,000 feet. And there are astronomers on board, and everyone who's flown on it reports an exciting adventure. At 41,000 feet, they have oxygen within reach in case the interlock between the telescope and the observers breaks. They have 15 seconds to get their oxygen masks on. The advantage of this telescope is that they can fly anywhere around the world, and they can fly anywhere around the world. They get up above the atmosphere, and we will have a report from Gordon Boryaker from Goddard Space Flight Center, who's reporting some of his results. I think
he's reporting.
We have two channels. One is a temperature channel, and one is a search for water. The temperature channel was truly dramatic, and we have very good coverage of both the G and the K fragments. After having looked at the G fragment, then we decided to set up the investigation a little differently. For the K fragment, we concentrated almost exclusively on the temperature. We wanted to make sure that we pin that down very precisely, and we have even better data for the K fragment. Going from the pre-crash signal level to the peak of the fireball, it went up by a factor of 25. So it was absolutely stunning. And since we have some spatial resolution, you can see all of Jupiter at once, and then in the limb of Jupiter where the fireball was, it's like seeing a supernova go off or a star go off. The main reason for using the Kuiper Airborne Observatory is that you're flying above 99.9% of the water vapor in the Earth's atmosphere, and you're above just 80% of the total atmosphere. Our key thermometer is the methane molecule, which is present in the Earth's atmosphere. By flying at 41,000 feet, this opens up a window where we can measure very strong methane features on Jupiter that are not measurable from ground-based telescopes.
Now, what's important here is that they're penetrating deeper into the atmosphere at 10 microns, and they are measuring emission lines from methane. So they're getting heated methane. There's evidence of heating of the methane clouds in Jupiter.
That's the methane gas in the stratosphere they're observing.
Okay.
It's not below.
Okay, so it's the stratosphere, the higher levels of the atmosphere. Okay.
And they're floating in our stratosphere as they do it.
That's right, stratosphere to stratosphere.
Okay. Now I think out of time, let's see. Well, the next images are from the IRTF at Mauna Kea, and those show. These are at 4 different wavelengths. We have in the 4 different wavelengths. At the upper left is the temperature in the upper atmosphere. The one on the right is ammonia, in a region of ammonia band. The one on the lower left is the region of methane, and the lower right is another ammonia region. Let's go on to the next one. We can take questions about that later. We've reported, have a report from Galileo that the photopolarimeter radiometer has detected the impact of fragment G, I believe, and they sent back some preliminary observations. These are not images, so I do not have a visual for that. But Galileo, we have data back from Galileo, and remember, Galileo is getting the direct straight line shot of these collisions, and the profile, the change in time of the intensity measured by the photopolarimeter will show us how the flash intensifies and the rate at which the flash decays. Then our last images are...
H, actually.
Okay, thank you. Then our last images are from a McDonald Observatory, and we have a report from Anita Cochran there.
we were able to get on it with both of the telescopes and start imaging. So we didn't actually catch the flash of L, but we were able to start looking at the morphology of the L site very, very quickly. The conditions turned spectacular very soon on. We had excellent, excellent transparency almost all the night, and extremely stable atmospheric conditions, so we have some really, really pretty images that we've gotten out with both an IR camera on the 2.7-meter telescope and a CCD camera on the 0.8-meter telescope. We've mostly been running around like giddy little kids because it's very exciting to watch this. We've all had to take our turns looking through the eyepiece because you can see the structure of the spots in the eyepiece in good conditions, and things are just changing, and it's so much fun to watch Jupiter change below our eyes. Image number 2 is a methane image taken with a CCD camera, and in this image we see a number of the spots, but one of the striking features of this image is that the H spot is just rotating onto the limb, and we've caught it in this image at a point where we see it detached from the planet. A hydrogen molecular band that is again observed with the IR camera on the 2.7-meter. In this we have 4 spots and the great red spot in the middle of the planet. We sent this in the conventional orientation. We find it amusing to turn this and some of the other images upside down and look at it. You'll see why when you see the image.
Okay.
That sums it up.
Thank you very much, Lucy. And if I can just sum up all the news we've heard today, or not all, but the high spots, we have the detection of the diatomic sulfur molecule S2, from the Hubble Space Telescope with the faint object spectrograph. Roger Yell told us about that. We have these wonderful auroral glows at the foot points of magnetic field lines in the north polar cap of Jupiter at a lower or more southerly northern latitude than aurora has been observed before. That was done in ultraviolet light, as explained to us by René Pranger with the Wide Field and Planetary Camera 2, and they know it wasn't there before because a few days prior they looked with the faint object camera, also in the ultraviolet. David Levy told us the G impact site is so extraordinarily prominent, wonders if maybe that's comet dust that's making it dark in visible light. The Keck telescope, we saw the hot impact spots still glowing in the infrared. There's still some heat there after some days after the first impacts. The first report back from the Galileo space probe, you're wondering why we told you you won't see anything for weeks from Galileo. That's images. These photopolarimeter measurements, the much lower data rate, you get it back pretty rapidly. Galileo at a distance of about 150 million miles, looking in the 9450 angstrom or 945 nanometers, sees the H spot. The Kuiper Airborne Observatory, the audio report from Gordon Yoracker told us about the heating of the methane gas in the stratosphere. And then Anita and Neil Cochran at the McDonald Observatory, Fort Davis, Texas, looking in the molecular hydrogen or H2 band. You see some glowing features and spots. You turn it upside down, and you have Jupiter doesn't seem so unhappy after all. Don?
Thank you, Steve. We're going to turn to question and answers here at Goddard, and I understand we have a lot of questions from our center, so I hope we have enough time on the satellite. We'll start here, front row, with Bill. Please state your name and affiliation.
Bill Harwood, CBS, and I'm maybe asking you if you'd maybe be more elementary in terms of the significance of the sulfur observation. If you knew that sulfur is in the atmosphere anyway, and you don't know where this sulfur comes from, I'm confused as to the significance of that. And also, I was reading a message on the internet yesterday from some other University of Arizona researchers who were claiming that they had done some studies or observations that indicated they were actually seeing cometary material, and I'm wondering if these two things are linking up somehow or they're totally separate issues.
Okay, first of all, we believe that there's sulfur in the atmosphere of Jupiter, although we hadn't detected it yet, just because the solar system has sulfur in it and Jupiter should not be an exception. However, that sulfur is deep in the atmosphere. It's in the form of hydrogen sulfide, we believe, H2S. And as you go higher in Jupiter's atmosphere, it gets colder, just like it does in the Earth's atmosphere. You form clouds. And the hydrogen sulfide should disappear into clouds at a fairly deep level in Jupiter's atmosphere. So just as an example, if potentially we could convince ourselves that this material was coming from Jupiter, not from the comet, that would tell us something about the depth to which the cometary fragments penetrated. I think maybe you're referring to the second part of your question. I think perhaps you're referring to an article that was in the New York Times this morning, I understood, on the internet? No. That the material was cometary? Well, I didn't see it, but what jumps out at us from looking at this, at least from the HST data, is that the molecules we've seen so far, ammonia and sulfur molecules, are things that are in the clouds of Jupiter. There's also an ammonia cloud in Jupiter.
The visible clouds on Jupiter that the amateurs see, those are ammonia.
That's right. And there's an ammonia hydrosulfide cloud, which is at a deeper level below 1 bar. There are other molecules associated with comets, oxygen. You might expect to see oxygen molecules, for example. We don't see any of those. What we see so far is things from Jupiter. And, well, you know, this is going to be a long story, but I don't understand that internet message.
I'm still awfully ignorant of chemistry. What is exciting? Bob Cook at Newsday. What is so exciting about finding this sulfur is why would the man in the street want to jump up and down about this?
Well, as I just said, it might tell you something about the impact itself. The particular molecule, to be perfectly honest, I don't know a lot about it because I didn't expect to see it. So it's a surprise. It'll be interesting to watch how this develops in time. One of the reasons this is interesting, I study atmospheres rather than comets, although I think comets are interesting too. But the best way to learn about something, not just an atmosphere, is to poke it and see what happens. So we just gave Jupiter's atmosphere a giant poke, and we're going to see how it develops in time, and that's going to tell us something about how atmospheres behave. It's going to add to our knowledge base of atmospheres, and that's going to be useful for our society. It'll help us understand the Earth's atmosphere ultimately.
I have a question to Dr. Bronger. You told us about the change of aurora of Jupiter. And do you have some example that the same thing happened to Earth in the past? And what is the meaning of your discovery from Jupiter to us, like knowing about the aurora of Earth and knowing about the meaning of the weather of Earth? And what, if something happened like Jupiter to Earth, what is the meaning for our life? I mean, like a shortwave transmission or something.
Well, I think what we see is the effect of the comet, the gas, or both, maybe the dust in the coma of the comet, which has been ionized, or the other option, the gas which has been ejected after the fireball, and it was very, very hot enough to be ionized. So these are the two options. In any case, we get some ions and electrons which are free in free space, and we know from the fact that they have been able to go along the field lines and to excite, to glow the aurora on the other side. We know that they have been put at very high energy. The kind of thing we can learn from that is the processes first the processes in the coma, how they can ionize, how they can be accelerated, and then how these particles are accelerated in the magnetosphere itself. This is a problem which is of high interest for plasma physics, and on Earth there are numbers of satellites which have electron guns, ion guns, which artificially accelerate ions and electrons to thousands of volts and see what happens at the footprint on Earth.
Of course, there were one or more experiments, I don't remember when, but the first one was authorized by President Kennedy to explode a nuclear weapon up in the magnetosphere and see the effect of the precipitating particles. It was a famous, was debated whether it would be safe or not, and finally Kennedy called Van Allen. He said it's his belts and it's all right. And I think the other part of your question was what would be the effect on the Earth. Well, of course, there might be a geomagnetic storm or something like that, but if a comet hits the Earth, then the effects in magnetosphere will be of secondary interest to many of us.
Well, I guess it wouldn't be a terrible effect because storms, it would affect communication, ionosphere, but even great, very strong magnetic storms from the effect of the solar wind, they do not affect life, just communications and broadcasting.
Question here.
Paul Hoverston, USA Today. Back on the sulfur question for a moment. Dr. Yell, if it turns out that the sulfur is from the comet and not the atmosphere, what would be the significance of that?
Well, it would tell you that there was sulfur in this comet, and eventually you might be able to figure out something about the abundance of sulfur in the comet. And the reason we study the abundances of comets is so we can understand comets are one of the building blocks of the solar system, or a remnant of a building block of the solar system. So you might be able to say eventually something about the composition of the early solar system. I should also point out that when you do observe comets, sulfur and other molecules in comets, you're seeing gas around the main body, and most of the mass is in the main body, and it's always difficult to try to infer something about the bulk composition from what you see in the coma, because there's chemistry that goes on and alters things and stuff like that. So what we just did is we just pulverized the comet to find out what was inside it, perhaps, and it's a different way to look at things.
Miles.
Hi, Miles O'Brien with CNN. I'd appreciate from anybody here sort of a little more of a layman's term explanation of what's going on in the magnetosphere of Jupiter here. I'm not sure that I'm real clear on what's going on.
I think what Dr. Pranget was talking about was that these are, of course, observations we've only just seen the last day or two, but the preliminary impression is that we have this big impact, the big splash, and the fireball on the southern part of Jupiter, and that this sends up some plasma, like the fireball that you saw. Some of this material gets electrified, loses the atoms or molecules, lose electrons, and then these...
they become charged.
Right. You have charged particles now, and I think the electrons in particular, probably you're talking about, they get accelerated by some forces that have to be worked out. But we know things like this happen on the Earth in other situations. They get accelerated, they travel to the other side of the globe of Jupiter and cause an aurora there at a place we've never seen before because it's further south. Whatever makes the aurora on Jupiter ordinarily doesn't bring it down that far south. It's like normally we see nice aurora in Canada and New England and so on, and it's a rare time when you see in Mexico City, although it does happen after a big flare.
The charged particles are constrained to move along these field lines, lines of magnetic field that you can see in the image. So they want to escape the atmosphere, but they can't. They have to move along these field lines and end up getting turned around and come back on the other side of the planet.
So if you were on Jupiter right now, you'd see northern lights like you'd never seen them before.
You'd be glad you were seeing northern lights and you weren't down south, actually.
One other thing, is there any evidence that you've seen over the last 24 hours which is settling one way or another whether this is a comet or an asteroid once and for all?
Oh, no. That's a very important question, but it's going to be very difficult to get an answer to that. So I'm afraid I just have to say flat out there's no evidence that will help us determine whether it's a comet or an asteroid.
Well, there may be evidence. We just haven't had enough time to think about it.
Exactly.
Would like to go to some of the centers for questions now, as we're going to run out of time on the satellite. Which first one up, please? Okay, well, we're holding on that. Is there one more here first? Right here in front.
Matt Crenson, the Dallas Morning News. For Dr. Yell, I don't want all the gory details, but in general, how can you tell whether the sulfur came from Jupiter or from the comet? And what are the chances that you'll be able to do that?
I don't know how good the chances are of it. To finally get the answer, we're going to have to correlate lots of different pieces of information. We'll have to, what we've seen so far as chemistry goes, are the molecules that are easiest to detect. With more work and with all the other observations being made, we'll undoubtedly hear about a lot more molecules. You look at the whole suite of molecules, that will help you. Try to infer something about the temperatures in the fireball, and that will tell you about the chemistry in the atmosphere. that'll help you understand what's going on. And by trying to correlate all this, I have hopes that we'll be able to say something about how much of the what we see is due to the comet and how much of what we see is from Jupiter itself. So I'm optimistic, but it's hard to put a number on the chances.
We'll be coming back to
Very
questions
optimistic.
here. Excuse me. We'll be coming back to questions here in a moment, but let's have one from JPL. Please state your name and affiliation.
This is Robert Lee Holtz from the Los Angeles Times. Two related questions. One, I guess I'm surprised to be hearing at this stage of the game that we're not sure this is a comet. Can you tell us why there's any question at this stage why this might be a comet or an asteroid? And then secondly, is it disconcerting to you folks that you're not seeing evidence of water yet?
Okay, I'll field that one. If Gene Shoemaker were here, he would say, oh, it's definitely a comet. And the probability of it being a comet, and Gene can argue persuasively that it's probably a comet. Dynamically, it is possible to give a gravitational push to an object anywhere in the solar system. And so dynamically, it's also possible to exert a gravitational force on an object in the outer region of the asteroid belt and perturb it so that it goes into orbit around Jupiter, as this object did. And we call it a comet because it was discovered as a diffuse object, which is the discriminating characteristic of a comet observationally. Now, it's a very important question to determine whether this was a comet or an asteroid, because the comets are remnants of the original solar system. They've been kept in cold storage for 4.5 billion years, and we can get a better handle on the starting material of the solar system if we're studying a comet. If we're studying an asteroid, the asteroids have been in the inner solar system. They've been subjected to higher temperatures. They've been subjected to greater frequency of collisions, and so the material is altered, and we just need to know what we're looking at.
And presumably, the reason you might, even though it's diffuse, you might think it could be an asteroid, is we know it's something that was fragmented by the tidal force of Jupiter.
We don't know what happened.
So it could be dust from this fragmentation and not an atmosphere like a comet has of evaporated or sublimed gases.
And the other question was about water. Are we surprised that we haven't seen water? Well, yes or no, yes and no. I appreciate the difficulty in analyzing the data from the Kuiper Airborne Observatory, and I continue to think of scenarios which would exist where water is there but we don't see it, and it may not be stable in Jupiter's atmosphere for long enough to get a detectable signal with the instrumentation, or it could be some chemical thing. So we have a lot to think about, and we also have to wait patiently and get some results back. Let the scientists analyze their data instead of showing us their raw images that have spectacular signatures on them.
Just a quick follow. Can you tell us what fragment we were looking at in the IRTF images?
Maybe. You always catch me on these questions on what image was it. Oh, actually, that was the A site. Remember A? Long time ago. So this is, they were observing A to watch for its evolution. It's very, we're going to become interested in how these things evolve with time. So that was the site of the first impact.
There are so many of these sites now that we've already seen reports where, as is swiftly pointed out by their colleagues, astronomers are saying this site looked like thus and so, and someone else says, no, at that time you looked, you were seeing a different site. There's so many of them now, you need a program when you go to the telescope to tell the spots on Jupiter.
Okay, we have some questions now from the Kennedy Space Center in Florida. Please state your name and affiliation.
Hi, Jim Banky of Florida Today. A question maybe for Dave Levy or Lucy. You said earlier in the week that you thought these spots would last for weeks, if not months. Is there any evidence from the ground-based observatories and telescopes that any of the earlier spots are fading away?
We're going to ask Lucy McFadden to answer that because Dave Levy was called away. He is in great demand.
There is evidence of fading of some of the spots, changes in the brightness of some of the spots. None of them have disappeared. Remember, some of the impacts didn't leave a scar. Fragment B did not make a significant feature.
The
So
Galileo,
there's some change.
Galileo people told us that besides spotting H, they looked for an impact site from B and did not see it with that photopolarimeter.
Okay, and the second question may be a little trivial for you folks, but in the forest of Jupiter, did the comet make a sound when it hits in? I know there's no one there to hear it, but did it make a sound? What would be the sound of a comet hitting Jupiter?
Very loud. I mean, made a very big sound. One of the things we'll be looking at for is seismic waves, which are a wave, as sounds are a wave. I don't think there's any conclusions on that yet, but it certainly did make a big noise.
Not just a sound, but it's a sonic boom that's going on there.
Oh, undoubtedly, yes.
This is Phil Chen, Earth News for Roger. How certain are you that this is sulfur? Have you eliminated all the other possible molecules? Is there any possibility that this might be from the Iotaurus or from the magnetosphere, some kind of ionized sulfur?
How sure are you that it's sulfur?
It's sulfur? Oh, we're absolutely sure it's sulfur. We, you saw that it had this very interesting structure where there were wiggles up and down, and there's about 30 of those wiggles, and they all line up with 30 lines expected from sulfur. And the distribution of intensities is also understandable in terms of sulfur. So I think there's no doubt. Now, I also reported a more tentative detection of H2S, and I want to be careful with that. The spectrum is consistent with hydrogen sulfide, but it might be possible to explain that feature with some combination of other molecules. We'll have to be more careful and wait and see on that. But for the S2, there's just no doubt. Couldn't be anything else.
The other part of Phil Chen's question was, could this sulfur be from the volcanoes on Io?
That's very hard for me to imagine. I think I'd have to say no.
Okay, and will you be making this data available on the internet? And using Heidi Hamel's analogy, how bad is the traffic jam on the information superhighway?
Traffic's very heavy on the information superhighway. I have reports that the computer up at Space Science Telescope Institute is jammed, stands still, just like Los Angeles. Our computer at University of Maryland, which is available for professional astronomers and the observers, has been running at 50 to 70% capacity, and we have anywhere from 1 to 2 dozen people on at any one time, and we cannot compute. We can't keep track of how many people log on, and the same at Hubble Space Telescope. They had to move their program that counts how many people are logging on to another machine because the machine couldn't handle the incoming traffic. So it's busy. It's the way it's supposed to be, I guess.
We'll go to headquarters now for some questions. Please state your name and affiliation. I'm not sure if we're having a technical difficulty.
Lost our time.
Headquarters, are you there? Okay, we're going to have time for one more question here, and I've been assured the panelists will stay around for questions later on. Let's go here, Mark.
This is Mark Carreau of the Houston Chronicle. Could you talk a little bit about Q, R, and S, and even the last fragments, and how they compare in size, brightness, or whatever with those that have hit before?
The Q, R, and S impacts will occur within about 10 hours of each other, which means they will land on Jupiter at the same location. Let's see, Dave Jewett at University of Hawaii has done some recent astrometry. He had an instrument which blocked out the light from Jupiter and allowed him to look at the fragments as they were approaching Jupiter very close. And with his measurements of the positions of the fragments, he enabled Paul Chodas and Don Yeomans at Jet Propulsion Lab to update the impact times. And those impact times have moved forward about 15 minutes. But the spacing between them, I believe, is still the same. So we're interested in watching what's going to happen when these sites land on top of each other, and it's going to make it harder for us to disentangle the information, but we may learn something from it as well.
Q should be big, right? I think that's part of the question.
Yeah, Q should be big. P should be big too. They're all big.
Let's try headquarters again. Go ahead, please.
Yeah, this is Ron Cowan from Science News. For Dr. Pronger, can you tell me how many kilometers this new footprint is below the existing one? And is there a way to understand why this cometary debris just getting onto the North Pole, why it wouldn't just brighten the existing footprint, why it would indeed create a new one? And again, how many kilometers beneath is it?
Well, the size in terms of kilometers, it's rather narrow in terms of latitude. It may be like, it's less than 1,000 kilometers in latitude. In longitude, it's elongated, and I would say probably like few thousand kilometers, maybe 10,000 kilometers. But out of that, we cannot tell whether it's a spot which has been moving on top of the planet, because the exposures have been 4, 5, 6 minutes long. During that time, a fixed spot in the magnetosphere rotates in front of the telescope by about 4 degrees, I guess. I'm not sure, but that's of the order. The spot itself, we have measured the trace, which is about 15 degrees. So in fact, it's longer than that. Either this is remaining light, and it has been created locally by the comet, but the comet, in the last 2 hours, the comet is going from the dusk side to the noon, at noon, and then to the morning side very, very fast. So if you have emission which is glowing for say 10 minutes, you will see it like a track on the observations. So we cannot tell so far how large is the spot, if it's a temporal effect, or if it is a special effect.
And the other answer to the other part of Ron Cowan's question, why doesn't it just shine in the normal auroral place, is that it's not like all the bees go to the same nest to get honey, but the magnetic line from the normal northern auroral zone doesn't come to the place where the comet hit.
The normal aurora comes from, apparently the last observation we got with the Hubble last year suggests very, very strongly, and the comparison with Ulysses, we did comparison with Hubble and Ulysses this year, and it's very strongly suggests that the normal auroral glow, we see it's related to currents which flow right at the limit between what we call the polar cap and the closed field line inside the magnetosphere. The closed field line, they rotate with the planet in 10 hours. The open field lines, as we say in our jargon, the one which are pushed away in the tail by the solar wind pressure, and which are open to the solar wind, normally they do not rotate with the planet itself. This creates the condition for strong currents, and there we see a sheet of precipitation. This is very, very high latitude, and it is connected at something like 60 planetary radius. The glow we have seen, this transient glow, is on field lines which go like 2 or 3 Rg at maximum at the equator from the center of the planet. Very, very close field line in what we call the inner magnetosphere. In the inner magnetosphere, normally, we do not have plasma to get this effect. And it was also connected to the path of the comet itself.
I think we have one more from headquarters.
Yes, this is Tracy Watson, U.S. World Report, I guess for Lucy or Steve. I'm wondering if you've seen any widening yet at the thin, dark ring from, can you hear me?
No, please repeat.
I'm wondering if you see any widening yet at the thin, dark ring from fragment G, the one surrounding the dark splotch.
That's for me?
Sure. It's a Hubble question.
Oh, I don't think we have any more results on that at this time.
Okay, that's all the questions we have time for today. We'll rerun the video and feed that on the satellite, and that's the end of the press conference. Thank you.
and start imaging. So we didn't actually catch the flash of L, but we were able to start looking at the morphology of the L site very, very quickly. The conditions turned spectacular very soon on. We had excellent, excellent transparency almost all the night, and extremely stable atmospheric conditions, so we have some really, really pretty images that we've gotten out with both an IR camera on the 2.7-meter telescope and a CCD camera on the 0.8-meter telescope. We've mostly been running around like giddy little kids because it's very exciting to watch this. We've all had to take our turns looking through the eyepiece because you can see the structure of the spots in the eyepiece in good conditions, and things are just changing, and it's so much fun to watch Jupiter change below our eyes. Image number 2 is a methane image taken with a CCD camera, and in this image we see a number of the spots, but one of the striking features of this image is that the H spot is just rotating onto the limb, and we've caught it in this image at a point where we see it detached from the planet. A hydrogen molecular band that is again observed with the IR camera on the 2.7-meter. In this we have 4 spots and the great red spot in the middle of the planet. We sent this in the conventional orientation. We find it amusing to turn this and some of the other images upside down and look at it. You'll see why when you see the image.
We have two channels. One is a temperature channel and one is a search for water. The temperature channel was truly dramatic, and we have very good coverage of both the G and the K fragments. After having looked at the G fragment, then we decided to set up the investigation a little differently. For the K fragment, we concentrated almost exclusively on the temperature. We wanted to make sure that we pin that down very precisely, and we have even better data for the K fragment. Going from the pre-crash signal level to the peak of the fireball, it went up by a factor of 25. So it was absolutely stunning. And since we have some spatial resolution, you can see all of Jupiter at once, and then in the limb of Jupiter where the fireball was, it's like seeing a supernova go off or a star go off. The main reason for using the Kuiper Airborne Observatory is that you're flying above 99.9% of the water vapor in the Earth's atmosphere, and you're above just 80% of the total atmosphere. Our key thermometer is the methane molecule, which is present in the Earth's atmosphere. By flying at 41,000 feet, this opens up a window where we can measure very strong methane features on Jupiter that are not measurable from ground-based telescopes.
For more information about the NASA STI program, please write to the NASA Center for Aerospace Information or call us at 301-621-0390.